HIRAM. So please start.
In the beginning, I would like to thank for all my colleagues and to preparing all the data, and also thanks to SJ and Lucas for the past 2 years cooperation for develop of the HIRAM. So this is the fifth talk about the HIRAM today. So but some of you probably not very familiar with the cube sphere. So this is the original cube sphere globe. But if we use a stretch in one tile, then the other side, the other tile, you will enlarge it, but still you have the same grid for each tile. So the only difference between the total grid numbers for stretch and non-stretch are the same, but because of the stability, so the time step in stretched HIRAM, you have to use a finer time step. Here, later I will use 3 different resolution. One is C192, that is about a half degree, and C384, that's about a quarter degree. And the other setting is C384, but stretched with factor 2.5. So this will be a variable resolution range from 10 to about 70 kilometers. So this is the cube sphere globe looks like if you center like in Taiwan. So this is how it looks like. So one tile you will have the finest resolution, and the other side you will have a very coarse resolution. But the total grid numbers are the same with the non-stretched cube sphere. And this is the setup we use in the C384 stretch 2.5 center in Taiwan grid, horizontal grid spacing. Here, this is the finest resolution region, so around 10 to 20 kilometers. And this is the coast resolution domain around 60 kilometers. So later we will focus on these 2 regions in the stretch grid experiment. Here we have 5 experiments, 2 half degree experiment for current climate and time slice experiment, and 2 quarter degree current climate and the future projection experiment, and 1 stretch grid variable resolution experiment. All these 5 experiments, the physics and the model setup are identical. The only difference is the time step. So it's 32 levels, not very high model top, just 10 hectopascal, and use the microphysics and shallow convection. And in the time slice experiment, this SST data is the same with the talk this morning, the MRI SST data. So first, I would like to show you the precipitation in these 5 experiments. It's a global pattern. This is the half degree, quarter degree, variable resolution stretch grid. This is the observation GPCP data. This is the difference, this minus this. And the table here shows its global mean and its correlation You can see that in these three experiments, these quarter degree simulation always have the better correlation than with the observation. But if you, and also the stretch grid experiment, the correlation is also not so bad, and the model mean is not so bad. But if you look into the local pattern, yeah, here we have too less precipitation in maritime continent and too much precipitation in this region. And this is the high resolution, the fine resolution region. And this is the coast resolution region. You can see we have too much precipitation here and too less in South America. So this is the lee side of the Andes mountain. And all three experiments, different resolution. This is about 50, 25, and 60 to 70 degree kilometer resolution. The too much precipitation in Andes mountain in three experiments are the same, but the lee side of the Andes mountain, the precipitation is too much less in this variable resolution experiment. And this is the boreal winter average. In GPCP data, you can see this a large-scale circulation makes the precipitation in here. And we have the same pattern in three experiments. But here, in the variable resolution, this is the fine resolution region. The circulation is strengthened and the precipitation is stronger here and weaker here. And if you go back to the two regions we are interested, you can see the same different pattern to these two experiments. And if you look into the JJA, again, this is totally different pattern to these two experiments. The same model physics, only different resolution. Here we have too less precipitation in this region and too much in this region. So if you focus on like Asian monsoon or MJO, the variable resolution stretch grid didn't perform very well. This compared to GPCP, we have too less precipitation here and too much here. And this is the OLR. Again, annual mean. Here we have too less cloud. And this is for summertime. Comparing to these two, the totally different pattern in these two regions. And when we tune the model, I don't know how to tune the model. You will judge by its global mean or regional effect, regional phenomenon, or yeah. But if from these three experiments, the global mean, not so much difference. But for regional climate, the performance is quite different. Yeah. So later I will talk about the typhoons and hurricanes. This is again the same experiment, 3 resolution setup. This is the best track data. Yeah, you can see here the typhoon numbers is much less than these two. Yeah. And this is the tropical storm annual variance. You can see the blue is the half degree setup. We tend to have too much hurricanes, typhoons. And this variable resolution one, the number is quite similar to the best track. But if you pay attention to this region, this is the coast resolution region. In these two resolutions, we don't have so many tropical storms, but here we have many in this coast resolution region. If you look more detailed to the typhoon density, and this is the Category 1 hurricane annual variance. If you look into this one, the C192, the half degree tropical storm numbers is higher than these two setup, even higher than the best track. But in Category 1 hurricane, the number of half degree resolution setup is not so many. So the resolution, if you improve your resolution in the model, it to help you to predict stronger typhoons, stronger hurricanes. But in HIRAM, probably you will have too many tropical storms. And this is the tropical storm density. In variable resolution, we have the finest resolution in western North Pacific, but we have too less tropical storms and typhoon and hurricanes. And because we are more interested in western North Pacific, so I will show a few more slides about western North Pacific. This is the best track density. You can see in variable resolution, the number is quite less comparing to the best. And this is the number comparing to best track and to the two different resolution setup. If you look into more detail to separate in different categories, so this is the red one is the variable resolution. In Western Pacific, it's about 10 to 20 kilometers. And the yellow one is the 25 kilometer quarter degree resolution and half degree for green. You can see for tropical storm, we have the half degree do have too many tropical storms. And only a few Category 3 tropical storm. But if you have used for higher resolution setup, you can have category 4 in our model. But when you use a 25 quarter degree setup, we cannot capture the category 5 hurricane. And this shows the hurricane precipitation in 500 kilometers box. So the stretched HIRAM tend to produce less rain than the other two coastal resolution. And in the future experiment, the time slice experiment. So this is the density. You can see the typhoons are less in our future projection. But comparing to the current climate simulation, the numbers are less, but the stronger hurricanes, the percentage of the stronger hurricanes are higher than the current climate. That means in our future projection experiment, the model tend to produce stronger but less hurricanes. And this is the correlation between the surface pressure and the surface wind. You can see in this stronger typhoon category in the future projection, we tend to have more than the current climate. And this is the other comparison with the future to the current climate. The same. In the future, we tend to have stronger typhoon than the current climate in the HIRAM experiment. Yeah. And I will also talk about the Asian monsoon, and this is the analysis done by my colleague Nicholas. And we have 5. This is the data we use in this Asian monsoon analysis. The Hagen couple model is a half degree, about 25 years data, and also have RCP 4.5 data. And the same, the HIRAM has half degree, quarter degree, and current climate and the future projection experiment. And also 30 semi-5 examples about 30 years, and also the future projection experiment. And also comparing these two with the unsampling analysis and the GPCP daily precipitation. So in May and June, this is the season for Meiyu. So if you, this is the difference between the semi-5 example and observation. So you can see the difference in this, the model cannot really reproduce the precipitation quite well in these 3 regions. And in June, July, and August, these Indian monsoon region and Western North Pacific monsoon region, the the model cannot simulate the precipitation quite well. So we will focus on these three regions in the following discussion. So this is the Meiyu region. So this is the accumulated precipitation. On the right-hand side this is the different months analysis, and this is more heavy rainfall, and this is the light rainfall. So Hagen, the UK Met Office couple model, the mean precipitation is okay, but overestimate the extreme. The Hagen is the red one. Yeah. And for HIRAM, we slightly underestimate the mean precipitation during summer and overestimate the extremes. And this is the current climate simulation in the Indian monsoon region. And Hagen has a back signal on mean precipitation here, and underestimate the extremes here. And for HIRAM, we have good signal on mean precipitation, and C384, the blue one, is better than the C192. And HIRAM tend to, both C384 and C192 tend to overestimate the extreme. And this is the western North Pacific region. Hagen has bad mean precipitation, and extreme seems to doing okay during summertime. This is the okay, and HIRAM also overestimate the mean precipitation during summer, and the extreme is really too high. And the index for these three regions, the Eastern Asia Summer Jet Index, we have four group of data, the NCEP to HIRAM and Hagen. You can see the Hagen has very good signal, the yellow comparing to the black NCEP data. And for RCP, the future, this is the future, one is current climate for solid line, and the future for dashed line. No much difference. But for HIRAM, we tend to, the quarter degree performs better than the half degree. But during winter time, the signal is too strong. And for the Indian monsoon region, the Webster and Young index, this is the Hagen has a very bad signal for this for Indian monsoon projection comparing to the NCEP. And HIRAM has very good signal, but in the future, the Indian monsoon will be weaker than the current climate. And this is a West North Pacific Summer Monsoon Index. The Hagen has good onset, but too strong in the summertime. And for future, the HIRAM, you can see the much weaker Western North Pacific index. So for skip this. Yeah, and this is I will show some more slides about the extreme precipitation, and thanks to Zhao for this analysis. And the methodology is to analyze the 30 degrees south to 30 degree north all the grid precipitation data and comparing with the trim with HIRAM C380 for the quarter degree experiment. And screen out the no precipitation data. That's about 70% in the trim and 50% in HIRAM data. So you can see the HIRAM tend to produce more extreme. This is the percentile from 1 to 100, but if you enlarge from 90 to 100 here, you can see the HIRAM tend to produce more extreme rainfall than the trim. And if we compare the HIRAM with the 12 CMIP 5 models, the same methodology, so you can see, but for heavy rain, the scale is different. Here is only to 160, here is to about 550. So for extreme rainfall, comparing to the CMIP 5 models, the HIRAM tend to produce more, much more than the CMIP 5 model. But the resolution is quite high. The HIRAM resolution is quarter degree, but here is the CMIP 5 model is 1 or 2 degree. And if you compare it to the rainfall frequency to the global warming trend, you can see when the air temperature is 1 degree higher, the HIRAM tend to produce more. This is the curve, its tendency to produce the change in frequency. Yeah, it's much different than the the CMIP 5 examples, but here is only to 100 millimeter per day, but HIRAM is to 200 millimeter per day. So you can see HIRAM has is more sensitive for extreme precipitation. So this is my summary. What I want to say is that this is, I consider this as the most important conclusion. In the very beginning part of my talk, the global pattern of our 3 different resolution setup. The variable resolution, even you have a very good global mean for the global pattern, comparing to the different resolution, the half degree or quarter degree. But if you look into a regional climate, it's much different. And because all the setup in different 3 experiments are totally the same, except the time step. So I consider the scale-aware parameterization should be applied for this kind of variable resolution GCM. I'll stop here.
Yeah, Dr. Singh. What do you think of the reason why you have the fewer storms over the Western Pacific in the stretch coordinate model? I think the resolution of the that Western Pacific region not much different from the uniform 50-kilometer version. Tropical cyclone, number of tropical cyclones is much fewer. Yeah. Yeah.
All I can think about the difference is the precipitation, the vertical convection in different resolution. You can see if you not look at only the numbers and look into the global patterns of the precipitation. So this is the summertime, the typhoon season. You can see here we tend to have less precipitation.
Do you know why?
Why?
But the difference between the stretch coordinate and the uniform 50-kilometer resolution, not much difference.
The parameterization, the physical parameterization are the same, but the parameter we choose is tuned from this setup. So we apply the parameters in this model, in this setup to
same physics but a different parameter?
The same parameters.
Same parameter?
But here, for Western Pacific typhoon region, here the resolution here is about 25 kilometer, but here is about 10 to 15 or to 20 kilometers.
But C190 to 50 kilometer.
These are 50.
So compared to that one, so why?
Totally different tuning.
Yeah, I mean, it's
Tuning?
the parameterization, the resolution affects the parameterization.
Okay.
So that's strictly totally
Yeah.
let's say 25. Yeah, but DAY1 totally Well, when you are variables, it depends on where you want to focus. So you can actually tune for that particular region if you want to do it. No, we didn't do that. Still doing global simulations.
Yeah, I'm wondering if the strengthening of the SPCZ, you know, if you look at the downward in this dry region, so it looks like it's a lot more precip. Is that possible? What is the resolution over those SPCZ reading? Is that pretty high?
So this is the horizontal grid spacing.
Right. Do you think over those maritime continent, if there is more precipitation, that might give the dry bias in those stretches? If the surrounding land, for some reason, get more precip, and then it could dry those regions that you've seen in. Do you see the over land actually get more precip over the maritime continent or along the East Asia compared with other?
You want to see the JJA or?
Whichever season give the largest dry bias in the stretch.
Yeah.
I think the other slides,
JJA,
right?
Yeah.
Yeah, this one.
Yeah.
So it looks like a source of those dry region. There's more precipitation. I'm wondering maybe that causes the dry bias of all.
Here, if you look at these dry bias, but this is wet bias here.
What about source of that dry bias? It looks like a lot more precipitation. Yeah, at the equator water. I mean, the total precip probably wouldn't change that much. If that get wetter, then the other region have to be dry.
So if we look to OLR, the summertime,
The OR basically goes with precipitation. So if you have dry bias, you will have that increase of OR.
I just want to make some comment about your tropical cyclones in the stretch grid model. I know we've had problems with a stretch grid. If you go from a coarse resolution to the high resolution, that you're, especially in the Western Pacific, where you have to get the lows forming in more of the Central Pacific before they propagate to the West Pacific. And that's maybe the resolution in that region is not adequate to start capturing the formation of the tropical cyclones before they move into the high resolution region. I mean, it's one possible idea. I think you have problems with your parameterization, as we discussed previously. It's probably more crucial to get the convective parameterization working at the high resolution. But another thing with tropical cyclones is that you're possibly not forming the tropical cyclones in the Central Pacific that propagate to the West Pacific as well because of the resolution change.
yeah, we should look into the genesis and do the comparison. We didn't look into that.
So thank you for the presentation this afternoon. To clap your hand to the 4 presentators. Yeah, thank you. And does any other business?
Thank you. Okay, today's sessions are all now finished. Thank you all for joining us today, and then we'll see you tomorrow at 9. Okay? All right, see ya. And all the guest speakers, please join us to the reception dinner at 6 at the lobby of the activity center. Thank you.